Good afternoon, everybody, and thank you for tuning in to Speed Control with DC Motor and PI Compensator. My name is Ty Reesner, and I did this project along with Justin Duke and Danny Bentley. And the three of us are seniors at Arkansas Tech University studying mechanical engineering. Today we would like to give you a brief introduction of what a DC motor is, the relative applications of those motors. In conjunction with this project, we did a design project for a DC motor and a PI controller. I would like to walk you through those parameters that we set as a group, show you the final results of that design, and then give you some of the concluding results of working with DC motors along with a PI compensator. One may ask, what exactly is a DC motor? From its name, you can see that it's a direct current motor. It converts electrical energy into mechanical energy. It's a DC motor, as you see in the diagram, consists of an armature, a commutator, and a stator. The commutator is connected to the direct current supply through the contact metal brushes that slide along the side of the commutator. The armature is connected to the commutator, which consists of coils of wire around an iron bar, and the stator surrounds the armature and is made of positively charged and negatively charged magnets that create a magnetic field. When the current runs through the armature, it comes into the magnetic field that is present from the stator. That magnetic field, along with that current, those two forces interacting with each other, create a push and a pull. The push and the pull forces from the magnetic field cause the armature of the motor to spin, thus turning electrical power into mechanical power with the torque that is created in that system. In that design project that our group was given by our professor, we set some parameters for ourselves, and we were going to design a speed control system with our DC motor. This speed control system could be for a motor vehicle, it could be really for anything, but we kind of narrowed it for a motor vehicle. The rise time for our system, we wanted to be within 0 to 2 seconds, something that was reasonable for a DC motor. We wanted our settling time to be from 2 to 4 seconds, nothing too crazy, but something that was obtainable. And then we wanted our percent overshoot to be between 0 and 5%. And you may ask, what exactly is the rise time? The rise time is the time required for a pulse to rise from 10% to 90% of the steady value. And the settling time is the time for the pulse to reach and stay within a range of plus or minus 2% of the steady value. And the percent overshoot just kind of gives you a percentage and quantification of the overshoot of the system, how far it overshoots that steady value with that initial pulse. So, like I said, we used MATLAB to model our DC motor, and the initial thing right here is the transfer function for the DC motor. It's a ratio right here of the output of the speed to the input voltage, and you can see the parameters that we used in MATLAB. J is 0.01, B is 0.1, K is 0.01, R is 1, L is 0.5. And right here I said S is equal to the transfer function of S, and then here's the open loop transfer function for the motor, the DC motor. And then in figure 1 we modeled it as a step function, which I will show you in the next slide. And the step function right here has, when it was modeled in figure 1, just for the DC motor alone, no compensators in it all, had a rise time of 1.14, settling time of 2.07. You're like, great, that falls within your parameters, but if you look at the amplitude of this, we only got up to 0.1, so we are about a factor of 10 off of the value we actually want, and we can't really see our percent overshoot here. So I'm going to show you what we did next. As a group, we decided we needed to put a compensator on this system so that we could get the desired parameters that we want. So we used the MATLAB defined function SISO tool that allowed us to utilize the root locus function for our open loop transfer function and make it a closed loop with negative feedback. And SISO tool is a great tool. I really recommend everybody looking into that and learning what it has to offer. And I'm going to take you over here to MATLAB and kind of show you what we did. So here's our initial function that we used in MATLAB. I modeled it, step function, And then as you can see, I added the CISO tool with the root locus right here. Come back here and see. Here is the CISO tool, what CISO tool provides you with. It shows you the root locus, and you can right click right here and you can set a design requirement. And if you see the design requirement, I have a design requirement of % overshoot, and you set that 5%, close that. So it's going to lock us in with a % overshoot of 5. And then we decided as a group we needed to install a controller on the system to make sure we got the output that we wanted out of our DC motor. So I right click right here, it shows our DC compensator. We introduced a PI compensator to the system, so right here you can add an integrator, a real zero. We add an integrator and a real zero. We set our real zero at -0.6, which is right here on our graph on the imaginary axis. And this is the root locus. Root locus really allows us to see our lines of constant damping ratio and our lines of constant % overshoot. So we can really see what design conditions we're working within and see our poles and our zeros of our transfer function. And right here, just kind of playing with these KP values, these proportional constants. If I start this out at 16, I can show you the results we get from that. And go ahead and look at the step response. We get a rise time of 1.172. We get a % overshoot. Back here behind that of 0. So that's our lower bound for our % overshoot, or 0. We wanted it to be from 0 to 5, and in that case, our settling time is 5.21. So that's a little bit too high of a settling time for us. So let's change this up to 30 and see what results we get when we change that. And we get a settling time of 3.54, a rise time of 0.195, and a % overshoot of 1.03. So if we change this one more time, go ahead. You can run multiple iterations of that. Change it to 35. Let's see what results we get. We're going to get our upper bound of a 5% overshoot, a rise time of 0.167, and a settling time of 3.2. So if you look at all those values, % overshoot, rise time, settling time, they all fall within our design parameters that we set as a group. So the root locus, very good tool along with the CISO tool that's defined in MATLAB. Very easy to use. You just got to adjust the values. You can use this compensator dial pad right here to really kind of set the parameters of your compensator and adjust those proportional constants, your integration constants, whatever you're using, if you're using a PID controller. But here's the upper bound with that overshoot of 5. That was our maximum % overshoot that our design parameters allowed us to have. And I'm going to show you our final results of instituting the PI compensator along with the DC motor. Our rise time came out to be 0.167 seconds. Our settling time was 3.2 seconds, so that fell between that 2 and 4, and then our rise time was between that 0 and 2 seconds that we desired. And then our % overshoot, like I said, is at our maximum bound of 5%, so that fell right where we wanted it. And then, in conclusion, DC motors can be modeled with MATLAB's open-loop systems or closed-loop systems. Using MATLAB-defined functions like the CISO tool allow you to put that negative feedback on there and put that compensator on there and model and really utilize the root locus and see how your system's going to change when you institute a PI compensator or a PID compensator to your system. DC motors can be used to operate shavers, blowers, lathes, drills, and many everyday devices that you use. You really don't use them, or you don't realize how many systems you're using on a daily basis that have a DC motor and a compensator with them. Thank you all for tuning in to this short video, and I hope you learned a lot.